A few minutes here. Okay, let us get started here. I thought today it would make a lot of sense to kind of go through this handout, which you should grab a copy of right back there. Let's see. Copy of the handout. Basically, for lack of a better description, it's kind of an integration flow chart. So this is if it looks like this, you should try this kind of thing first. And then if it doesn't work, try this other thing next. And that's generally how the process of trying to anti-differentiate or integrate something works in general. You try something, it doesn't work, you try something else. Please grab a handout. So we'll go through this list. We're going to spend more time on the later stuff because that's kind of the harder stuff, but we should remind ourselves of kind of all the methods we have available to ourselves on how to anti-differentiate something. So there's kind of three broad categories here. There are, okay, fine. There are algebra integrals, meaning you don't have anything other than powers of x, square roots, cube roots, but you don't have any logarithms, exponentials, trigs, inverse trig, no other types of functions other than just powers of x in lots of different ways. Then you have trig, which means, you know, sine, cosine, tangent, secant, cosecant, cotangent, and all of their various ways of combining those things together. And then lastly, and kind of largely, we have mixtures. which usually lend themselves to being done either with a U substitution or with integration by parts. So those are kind of the three categories. And honestly, the first category is the biggest one. The algebra integrals take up a lot of the, I should say it's the biggest as far as the number of methods we have of approaching those integrals. We have lots of methods to try to integrate quote unquote algebraic integrals. So let's kind of look at those. I'm going to follow along with this little handout. For those of you on Zoom, I did post an announcement that everyone should take a look at this handout if you're on Zoom. So you can, if you go to the announcement, you can find the link, or you can just go to the modules at the very bottom of the modules. You should be able to find the handout that looks like this right there. It's called the, I think I wrote it as like integration methods, parentheses long is the one I am looking at. So let's take a look here. So the first question is, can you make it an exponent problem? And when I say the first question, I mean, the first thing I'm asking myself if I'm trying to figure out how to integrate something is, can you just write it so that you have a bunch of x to powers? For example, if I had something like, so, and I'm gonna write some of this, but not all of it. So the first thing we're gonna do here is we're gonna have the algebra section. And then the first part is, can we make the integral an exponent problem, meaning powers of x. So something like this, and I'm going to change the example slightly from what they have here, just so that you can also have those examples to refer to, and then the ones right here will be a little bit different. You could have something like, for example, 3x plus 5 squared. Let's kind of start with that. And in this case, we can just multiply it out. We can write this as the integral of 9x squared plus 2 times 3x times 5 is going to be 30x plus 5 squared. And then we can differentiate that. We get 9x cubed over 3 plus 30x squared over 2 plus 25x plus c. And yeah, we could simplify that. That's 3x cubed. That's 15x squared, but it's fine. Or you might have something like the integral of x cubed plus 2 square roots of x plus 1 all over 3x squared. And then the idea is we can still simplify this to make it a quote unquote exponent. We can write this as each thing divided by, in fact, before I do any of this, what I should really do is I should pull out the 1/3 and write it as 1/3 times x cubed plus 2 root x plus 1 all over x squared. And then divide each term by x squared to get 1/3 times the integral of x cubed divided by x squared is x. 2x to the 1/2 divided by x squared is going to be 2 times x to the 1/2 minus 2 is -3/2. And then 1 over x squared is x to the -2. And then we can just use the anti-power rule. So we're going to get 1/3 times x squared over 2 plus 2 times x to the -1/2 divided by -1/2 is the same as multiplying by -2. And then plus x to the -1 divided by -1. And we could simplify, but again, I'm not so much focused on the simplifying here as just the doing. So typically, if we can just simplify it and then directly anti-differentiate it using formulas we know, that's great. I should point out, even though it's not an algebraic thing, this also applies for other types of integrals, meaning if you can just multiply it out and see that things look like derivatives of things you already know, that's totally valid. So as kind of an aside here, if, for example, someone said, I want you to do the integral of secant x times secant x plus tangent x. Well, if you multiply it out, you get the integral of secant squared x plus secant x times tangent x. And those are both functions that we recognize as derivatives of known trig functions. The integral of secant squared is just tangent, and the integral of secant x tangent x is just secant x plus c. So more broadly, if you can simplify something and see how to anti-differentiate all the parts straightforwardly, that's what we should do. But that's not always or even often going to work. but it's still something to keep in mind. The next thing to typically consider is, and again, we're still kind of limiting ourselves to just algebraic things, meaning just powers of x. Does the derivative of one part equal another part? So this is the next question I usually ask is, does the derivative of one part equal another part? This question is the setup for wanting to use a U substitution, right? If I can say yes to this question, it usually means that doing a U sub is probably a good idea. For example, I could say the integral of 6x plus 2 over 3x squared plus 2x plus 5. In this case, yes, the derivative of, I wouldn't normally write this, but the derivative of the denominator is exactly the numerator. So if the answer is yes, then try a U sub. So here we would let U equal 3x squared plus 2x plus 5. And our du would equal the derivative of that, which is exactly 6x plus 2 times dx. And so we then could rewrite this as the integral of du over u. And the antiderivative is the natural log of the absolute value of u plus c, which is the natural log of the absolute value of 3x squared plus 2x plus 5. Let's see. I'll also point out, it doesn't have to be a perfect one-to-one match, right? If you pick a u and its derivative is off by a constant multiple, that's still fine. For example, I think it's another example. I can wait. So, another example. If we have the integral of, say, x squared over x cubed plus 5 to the 11th power. Well, the answer to my question, does the derivative of one part equal another part? The answer is still close enough to yes. If I let u equal x cubed plus 5, du is equal to 3x squared dx, and being off by a multiple of 3 is close enough. There's the only thing I don't love about U substitution here is there's like 3 different ways people like to do this. If it's me doing it, I'm going to do the thing where I say 1/3 times du equals x squared times dx. That's the way I like to see it because I see the x squared times dx in my. But other people like to multiply this by a 3 and a 1/3. Other people like to say that dx equals du divided by 3x squared and then cancel the x squared. Those are also both valid. It's just not the way I like to do it. But if you like doing it that way, that's really totally fine. So I'm going to do it this way. I'm going to say I have the integral of 1/3 times du divided by my u to the 11th power. And then this becomes a rewriting exercise. We're going to write this as 1/3 the integral of u to the negative 11th du. And if I differentiate and get u to the negative 10 divided by negative 10 plus c, plugging back in that u is equal to x cubed plus 5, we get negative 1/30 times x cubed plus 5 to the negative 10th plus c. So those are the kind of nice things that can happen if it's just powers of x. But then there are lots of less wonderful things that we also might get stuck with. So a few examples of these, of this next category, which I'm going to broadly, well, I didn't pick this, which is broadly titled tricks. Other methods, things that are tricky maybe. So one trick that you might have already seen is to try long division. So long division, if the degree on top is bigger than or equal to, I feel like people miss the equal to part a lot on this, the degree on the bottom. So a couple examples of this would be something like the integral of x cubed divided by x minus 1. It's almost too easy. So I will point out that's not too easy, but I would do long division here, although there is another method that's also applicable, which we'll kind of come back around to in a bit. If we do the long division, x minus 1 into x cubed, x times x squared gives me x cubed, and then x squared times negative 1 is negative x squared. Subtract, nothing minus minus x squared is positive x squared. What do you multiply by x to get x squared? It's x times x is x squared. X times negative 1 is negative x. Subtract, you get a positive x. And then x goes into x one time. 1 times x minus 1 is x minus 1. Subtract, and you have a 1 remainder. So then we can rewrite the integral as the quotient, x squared plus x plus 1, plus the remainder divided by the divisor, 1 divided by x minus 1. And then we can anti-differentiate this. We're going to get x cubed over 3 plus x squared over 2 plus x plus the natural log of the absolute value of x minus 1. We'll see. When your denominator happens to be a linear function of x, like u equals x minus 1, u equals 2x plus 3, there is a different route we could also take, which, depending on your perspective, you might like better or less. Better or worse. Anyway, just to see one more example here, if we had something like, I'm going to make something up, it's probably going to turn out to be less nice. But for another example, if we had, say, the integral of, I want this to come out not terribly, but fine, I'll just make it up. 2x plus 3 over x minus 5. This is a great time to do polynomial division. The degree on top is bigger than or equal to the degree on the bottom. And it actually comes out really, really nicely. If we do this, 2x plus 3 divided by x minus 5, it's only a one-step polynomial division because the degrees are the same. So we have a 2 up here. 2 times x minus 5 is 2x minus 10. Subtract, 3 minus minus 10 is 13. So we can rewrite the integral as the integral of 2 plus 13 over x minus 5. And then that's going to be 2x plus 13 times the natural log of the absolute value of x minus 5. We'll see. Okay. So that's something we can try. Sometimes when we do long division, then the remaining fractional or quotient part still requires other methods, like partial fractions or something else. So let's talk about the second trick, which is partial fractions. When I think of these tricks, I also kind of think of them as methods of later resort, right? I'm definitely going in order. First, I would try to simplify. Then I would try use sets. Then if the degree on top was bigger than or equal to the degree on the bottom, I would try long division. And then if I had something that I could try partial fractions for, I would try that. So for example, if we have something like the integral of 3x plus 1, some of these examples I am using as they are because I don't want to come up with something that's totally terrible. But if we have something like this, well, I can't simplify it. U sub's not going to work out great here because if I let u equal the bottom, the derivative of that is 2x plus 4, which certainly is not a multiple of 3x plus 1. I can't do polynomial division, so I look to see, can I use partial fractions? So can I factor the denominator here? And the answer is yes. So can I factor the denominator? The answer is yes, then we can try partial fractions. So we take our integrand 3x plus 1 over x plus 3 times x plus 1. We set it equal to a over x plus 3 plus b over x plus 1. We multiply both sides by the common denominator, x plus 3 times x plus 1, to get rid of the denominators. On the left-hand side, we're left with 3x plus 1. Right-hand side, we have a times x plus 1 plus b times x plus 3. And then I would always recommend using the convenient values of x. So if we let x equal -1, we're going to get 3 times -1 plus 1 on the left. We're going to get a times 0, which I'm not even going to write. And we're going to get b times -1 plus 3. So then we have -3 plus 1, so -2 equals b times +2. So b is equal to -1. And then if we plug in x equal to -3, the other convenient value, on the left-hand side, we have -9 plus 1. On the right-hand side, we have a times -3 plus 1 plus b times 0. So -8 is equal to a times -2. So a is equal to 4. And then we go back and we rewrite the integral as the integral of the a value we just found, 4 over x plus 3, and the b value we just found, -1 over x plus 1. It would be fine to write this as 4 over x plus 3 minus 1 over x plus 1. I just happen to not write it that way. And then we integrate. We get 4 natural log of the absolute value of x plus 3 minus 1 times the natural log of the absolute value of x plus 1. Let's see. Partial fractions. Interesting. Yes, there are lots of other things that can happen in partial fractions, but kind of the guiding light there is that if you've gone through those other 3 things or 4 things and none of them seem to be applicable, and you can factor the denominator, then trying partial fractions is worthwhile. Sometimes you can't factor the denominator. Like, well, I'm gonna leave off the name of this for a second. I will put it in. Like, for example, 1 over x squared plus 6x plus, I don't like that number. I'm gonna pick a different number. 13. 13? Yeah, 13. Cool. Definitely does not factor. And when I say does not factor, so it's annoying because what I really should be saying when I say does not factor is doesn't have any real zeros. So technically, although it's annoying and hopefully no one would ask you this, if you were faced with the integral of, like, say, 1 over x squared minus 7, you could do that integral using partial fractions, where you would write 1 over x squared minus 7 is equal to a over x minus root 7 plus b over x plus root 7. And that is really the only way to do that one. Yeah, it's annoying, which is why hopefully no one asks it. But the point is that I'm not saying that, like, technically this factors because it has real zeros. So when we say something doesn't factor, what we really mean is if you set that equal to 0 and try to find solutions, you won't have any real solutions. They will be imaginary. And when that's the case, completing the square is on the table. So if I try to complete the square here, let's see what happens. Well, I'm going to get integral of 1 over x squared plus 6x plus 6 over 2 is 3. 3 squared is 9. And then I could say minus 9 plus 13, or I could just say minus 9 plus 13 is 4. There's the same integral written with a completed square. And then I'm going to rewrite that as the integral of 1 over x plus 3 squared plus 4. And then we can do a u sub. Depending on how you feel about this. I feel like we could, this one's kind of weird. Like, sorry, I'm very kind of wish-washy here. Like, how much work should we really do? I think, sure, let's start with the u sub. If you let u equal x plus 3, your du is dx, and we can rewrite this as the integral of 1 over u squared plus 2 squared, which I think you're allowed and welcome to memorize the answer to. But if you're not, there's more we can do here. You could do another u sub, which is terrible, and say, I'm going to write this as, well, first, before I do that, I'm going to factor out the 4 on the bottom and say I have u squared over 2 squared plus 1. The reason I'm doing this is to try to get it to look like 1 over something squared plus 1, because I know that the antiderivative of that is the arctangent of the something. I feel like I'm doing too much work here to do this, but so be it. So then we would rewrite this as the integral of, 1/4 times the integral of 1 over u over 2 squared plus 1. And then we do another u sub. We'd let w equal u over 2. dw is 1/2 du. 2 dw is equal to du. And we rewrite this as 1/4 the integral of 1 over w squared plus 1 times 2 dw. So then we get 2 times 1/4. And finally, the integral of 1 over w squared plus 1 is the arctangent of w, which is then the arctangent of u over 2, which is then 1/2 the arctangent of x plus 3 over 2. But in reality, what I would say is that we get to be allowed to know that the integral of 1 over u squared plus a squared du is equal to 1 over a times the arctangent of u over a. So when I saw that this was written as 1 over x plus 3 squared plus 2 squared, I was thinking, oh, I'm going to get 1 over 2 times the arctangent of x plus 3 over 2 plus 3 as my antiderivative. But that kind of depends on your appetite for how much you want to remember and how much you want to do. I will say arctangent integrals that end up being arctangent come up often enough, especially with trig sub kind of stuff and partial fractions, that it's probably worth memorizing that rule or that formula that the integral of 1 over u squared plus a squared is 1 over a times arctangent of u over a. Yeah, I know. It's not everyone's favorite. So completing the square can be kind of not everyone's favorite. That's all. That's really, as you might have guessed, it's not my favorite. But it is something that comes up sometimes, especially if you're leading into a trig substitution possibly. So this one, I will also mention, we could have done the trig sub, but I'm trying not to do a trig sub unless I have to, right? That's a method of also later resorts. Speaking of trig subs, that's kind of the, not the last. So as you can see, there's a lot of algebraic methods here, right? So for trig substitution, you're using a trig sub if we see something like the square root of a squared minus x squared, the square root of x squared minus a squared, or the square root of x squared plus a squared. For the x squared minus a squared one, you're going to let x equal a times sine theta. For the x squared minus a squared, you're going to let x equal a secant theta. And for the x squared plus a squared, or a squared plus x squared, you're going to let x equal a tangent theta. Those are always the trig substitutions that we're trying. So for example, I don't love this example. Let me pick a different example. Where'd you go? Sorry, I have them here. Sure. For example, the integral of 4 over the square root of x squared minus 1. So in this case, we would let x equal secant of theta. And the reason we're making that choice is because if we plug in that choice for x, the inside of the square root will become a trig identity. I feel like people are having a little bit of a hard time seeing what I'm writing. If you ever need me to clarify something, please don't hesitate to ask. Our dx is going to be secant theta times tangent theta times d theta. And then we're going to start replacing things. This is going to become 4 divided by the square root of secant squared theta minus 1 times our dx, which is now secant theta tangent theta d theta. We're going to simplify. The whole point of doing this was so that the inside of the square root becomes something that we can get rid of the square root. Secant squared minus 1 is equal to tangent squared. So we're going to end up getting the integral of 4 times secant theta times tangent theta divided by the square root of tangent squared theta, d theta. And as long as you're doing an indefinite integral, you don't really have to worry about the absolute value stuff. If it's definite, sometimes you do have to worry about some absolute value stuff. So here we're going to get the integral of 4 times secant theta times tangent theta divided by tangent theta. And we're just going to cancel those tangent thetas. And then the integral of 4 times secant theta d theta, so as I could have pulled the 4 out, is going to be 4 times the integral of secant theta is something you do need to memorize. It's going to be the natural log of the absolute value of secant theta plus tangent theta. I do appreciate that the derivative of secant theta is secant times tangent, and the antiderivative of secant theta also has secant and tangent in it. It's the natural log of secant plus tangent. So it's, I mean, it's not the same at all, but it's still like, you can kind of make a connection there that the derivative and the antiderivative of secant at least have the same kind of pieces in it. And we're not done because we started an indefinite integral with x's as our variable. We better end with x's. So this is where we use the triangle thing. We say, great, secant of theta is equal to x, which is really x divided by 1. And secant is which side over which side? Here's what I really know. I know that secant is the reciprocal of cosine. I know that cosine is adjacent over hypotenuse. So secant better be hypotenuse over adjacent. But that's really the thought process I go through. I never remember like secant is hypotenuse over, okay, if you say so, hypotenuse over adjacent. But really, it's the reciprocal of cosine. That's how I'm doing it. So secant is hypotenuse over adjacent. And then the remaining side, we can use the Pythagorean theorem for, but it should always be the square root that made you do the thing in the first place. It has to be the square root of x squared minus 1. Also because the square root of x squared minus 1 is equal to tangent theta. And if you look at here, tangent theta is opposite over adjacent, which is the square root of x squared minus 1. So it really, really, really is true. Here you probably could have actually not drawn the triangle and figured it out still, because technically your tangent theta is right there. You can be like, oh, it's x flat, but I like drawing the triangle. So we get 4 natural log of the absolute value of secant theta, which is x, plus tangent theta, which is the square root of x squared minus 1. The example that I didn't want to do that's in the notes here, I didn't want to do because I think it actually is done better a different way, which we haven't quite gotten to yet. So we'll come back. There is a method we're about to get to. It's not 5. I think it's method 6. Or no, it's not in here. Interesting. There's one method that's missing from this list. I find that disappointing. I will add it in. Don't worry. Yeah, that's funny. I'm surprised that that's missing. So 2 more methods. I'm going to add in one here. This is going to be 5a. U sub with a back sub. So sometimes U sub is the way to go, but you've got leftover x's. For example, the one that's actually in the notes here, the integral of x cubed plus times the square root of 4 plus x squared. It's debatable if this method is easier or not. I think it definitively is, but other people would maybe argue that it wasn't. I think they're wrong. I'm going to try letting u equal 4 plus x squared instead of jumping straight to the trig substitution, x equals 2 tangent theta. If I do this, my du is equal to 2x times dx. And while I don't have a 2 times x times dx, I do have an x. It's hiding in the x cubed there. So I can think of this as 1/2 times du, excuse me, equal to x times dx. And I can rewrite my integral as the integral of breaking up the x cubed as x squared times x. And then also there's the square root of 4 plus x squared there. I can think of this x dx as being equal to 1/2 times du. This square root of 4 plus x squared is the square root of u. And the leftovers here, I can solve for using my choice of u. If I solve for x squared, u minus 4 is equal to x squared. And then this becomes, I think, relatively straightforward, or at least simplifiable. This is going to be the integral of u minus 4 in parentheses times the square root of u times 1/2 du, which I would rewrite as 1/2 times the integral of u minus 4 times u to the 1/2. Distribute the u to the 1/2. Get 1/2 times the integral of u to the 3/2 minus 4u to the 1/2 du. And then we can anti-differentiate. We get 1/2 times u to the 5/2 times 2/5 minus 4 times u to the 3/2 times 2/3. Let's see. Plug back in what u is equal to. Maybe distribute the 1/2 as well and get 1/5 times 4 plus x squared to the 5/2 minus 4 times 1/2 is 2. 2 times 2/3 is 4/3. 4/3 times 4 plus x squared to the 3/2. Let's see. Interesting. I'm intrigued here because I'm looking at the answers here, and they are slightly different, and I'm not sure where that 30. I feel like that's a mistake there. Yeah, I think that I'm gonna have to look back over these. So this is not something I wrote. Something a coworker of mine wrote, and there might be an error or two that I will look for later. But yeah, I feel like there's something going on here. Anyway, this is not incorrect unless I made a mistake, obviously. But I think this is an easier path than doing the trig sub and then going back and finding what theta is equal to and all that kind of stuff. So if you can do a u sub with a back sub, it's often not a bad choice. In fact, there was another integral that we already looked at before that would have lent itself to this. The example we did, we can look back here real quick. Actually, the first long division example we did. So this integral here of x cubed over x minus 1 dx, you can also do a u sub with a back sub here. If you let u equal x minus 1, your du is dx, and then your x is equal to u plus 1. So you can rewrite this as the integral of u plus 1 cubed over u du. You do have to multiply at the top, which can get kind of gross depending on how big that power is. And it might not be the right choice sometimes. But here we have u cubed plus 3u squared plus 3u plus 1 divided by u du. Divide each thing by u, u squared plus 3u plus 3 plus 1 over u. And then we integrate and we get u cubed over 3 plus 3u squared over 2 plus 3u plus the natural log of the absolute value of u, c. And then they plug back in that u is equal to x minus 1. And we get x minus 1 cubed over 3 plus 3x minus 1 squared over 2 plus 3 times x minus 1 plus natural log of the absolute value of x minus 1 plus c. Now, if you look at the other answer we got, this actually looks quite a bit different. I'll point out, here's the answer we got before. Maybe. Right there. So if you actually multiplied all this out, you would get a 1/3 x cubed. You would get a 1/2 x squared because the coefficient of x squared here and the coefficient of x squared here would come out to be 1/2. And you would get a 1x, but then the constant term that you would have here would probably not be the same as the 0 constant term you have here. And that's okay. It's fine for your integrals to differ by a constant. So these really are the same, except they might be different by a constant. but they don't exactly look the same at first sight. But they are the same, I promise. You can multiply it out if you really want to check. But no one really wants to check. So, okay, let me get my papers back in order here. Very all over the place. Well, I'll fix it later. Okay, so that's U sub with a back sub. And then the final kind of algebraic method we have is what people call algebraic substitution or sometimes power substitution. So algebraic or power substitution. Really what I think of kind of this is you're trying to make the U sub work. Like you've kind of run out of options and U sub seems like the only plausible thing. So one example of this is something like the integral of the square root of 1 plus the square root of x dx. We don't have many options here. Like only one option is a U substitution. It's definitely not, right? There's no polynomial division. There's no partial fractions. There's no trig substitution, right? There's really nothing here other than try a U sub. So we try U equal to, I'm going to pick the insides. 1 plus the square root of x. And you might notice that finding du is not going to help us. If I take the derivative of both sides, the derivative of x to the 1/2 is 1/2 x to the negative 1/2, or 1 over 2 square roots of x. I don't have that in my integral. So if that happens, I kind of abandon this direction. So not this. Instead, take your u equal to 1 plus root x and solve for x. So we're going to say that u minus 1 equals the square root of x. And then u minus 1 squared equals just x. And then differentiate both sides of that. So the derivative of u minus 1 squared is 2 times u minus 1. And then we have a du equal to the derivative of x is a 1 times dx. And then we can start replacing things. So we can rewrite this integral as the integral of the square root of u times my dx, which is equal to 2 times u minus 1 times du. I'm going to bring out the 2. U to the 1/2 times u is u to the 3/2. U to the 1/2 times 1 is u to the 1/2. Now it becomes a direct antiderivative or antiparable problem. We get 2 times u to the 5/2 times 2/5 minus plus u to the 3/2 times 2/3. C, and then we plug back in that u is equal to 1 plus root x to end up getting 4/5 times 1 plus root x to the 5/2 minus 4/3 times 1 plus root x to the 3/2. Plus C, thank you, good call. So that is a fairly exhaustive, but I'm sure you can come up with some other weird stuff. But that's a fairly exhaustive list of all the algebraic types of things we can do. And then there's 2 other whole categories. So before we move on to the trig stuff, sorry. Is there any time that U sub with a back sub is not going to work as replacing trig sub? Yeah, definitely. So U sub with a back sub only works kind of if the powers are nice. So like for example, if that question that I did the U sub with the back sub, again, sorry, notes all over the place here. You're gonna have to be careful when I put these back together. That was the previous page here. Sorry, everything's everywhere all at once. Okay, I think I found it, maybe. Right, so here, if this problem had been the integral of x squared times the square root of 4 plus x squared, I couldn't have done a U sub with the back sub because I would have needed one of the x's to get soaked up in the du, and then my other leftover x would have been the square root of u minus 4. I mean, no, that's not going to work out. So usually U sub with the back sub is not necessarily going to work, but I guess the pattern I've noticed over the years is that if you can make a choice for u that's the power of x, And double that power minus 1 is also showing up. Then that's a plausible choice. Let me show you what I mean, just to give you one more example. So let's say we had something like the integral of powers. Sure, the cube root of x to the 4th plus 1 times x to the 7th dx. You can barely see. That's a good candidate for a u sub with a back sub, because I know that my du is going to be something times x cubed. That's going to pull off 3 of those x's, leaving how many behind from the x to the 7th? 4 of them, and I'm going to have an x to the 4th, so that seems like it's going to work out okay. So here, I would let u equal x to the 4th plus 1. My du would be 4x cubed dx. My 1/4 du is going to equal x cubed dx. I'm going to rewrite this integral as the integral of x to the 4th times the cube root of x to the 4th plus 1 times my x cubed dx, and then things are looking pretty great. X cubed dx is equal to 1/4 du. X to the 4th plus 1 is equal to u, and x to the 4th is equal to u minus 1. So if you see that kind of pattern showing up, where the thing you might choose for u, the power of x you're choosing, double that power minus 1 is also in there, that usually works out pretty nicely for a u sub with a back sub. So this would end up being the integral of 1/4 times u minus 1 times the cube root of u, which then you would multiply out. You get 1/4 times the integral u to the 1st times u to the 1/3 is u to the 4/3 minus u to the 1/3. And then it's just anti-power rule stuff for the umpteenth time. You get 1/4 times u to the 7/3 times 3/7 minus u to the 4/3 times 3/4 plus c, and then you plug back in u equal to that, and you get your final answer, which I think you all can do on your own. Plug back in u equal to x to the 4th plus 1. So those are all the kinds of things we can do if we just have algebraic things, right? Powers of x and no trig, e to the x, natural log of x, inverse trig function, right? We haven't dealt with any of that. So that's what the other 2 categories are for. The second category being trig. So I will say, I really mostly want to talk about the first category because that's the category that we've kind of introduced relatively new methods in the last week or so, with the partial fractions and the trig substitution specifically. But just as kind of a recap, category 2 here, losing my mind. Sorry, I should have stapled this. The staple one's over there right now. The trig. Just trig. There's a lot of things you can do. Typically, we're thinking u substitution. So, I mean, there is this first part. Okay, fine, we'll do this first part. So, is it a u sub? Personally, I don't think you need to do a u sub for the integral of sine of 3x. I think you all can do that without doing the u substitution and get negative cosine of 3x divided by 3. But if you want to take the longer route, that's also fine. We could let u equal 3x, or du is 3 times dx, or 1/3 du is equal to dx. And then we can write our integral as the integral of sine of u times 1/3 du. We get negative cosine of u times 1/3 plus c. And then we plug back in what u is equal to, and we get negative cosine of 3x divided by 3. Let's see. But again, for those mini u substitutions where you're just letting u equal a multiple of x, I think you can bypass that. And then if you have, well, really there's kind of three categories here. If you have powers of sine and cosine, the usual thought process is to try to do a U sub and to make the choice where your non-U thing has an even power left over. So for example, if I was doing the integral of sine cubed x cosine squared x dx, I would let U equal cosine because my du will be negative sine. And after I pull that part out, I'll have an even power of sine left over. That is always my goal if I have powers of sine and cosine or secant and tangent or cosecant and cotangent. So if I do this here, I'm going to let U equal cosine of x. My du is negative sine x dx. My negative du is positive sine x dx. So this becomes the integral of sine squared x times cosine squared x times sine x dx. And my sine x dx is my negative du. My cosine squared is just u squared. And using the trig identity, we can say that sine squared x is equal to 1 minus cosine squared x, which is going to equal 1 minus u squared. So then we end up with the integral of 1 minus u squared times, let's make that a negative u squared times du. If we multiply it out, we get negative u squared plus u to the fourth that we're integrating. We get negative u cubed over 3 plus u to the fifth over 5. Let's see, and then we plug back in u equal to cosine. So we get negative cosine cubed x over 3 plus cosine to the fifth x over 5. Let's see. So that's your guiding principle for powers of trig functions, essentially. If it just, so I should really say, if it's sines and cosines, or secants and tangents, or cosecants and cotangents. But like if you have like sines and tangents or cosecants and secants, and like if you have a more of a mixture of trig things, usually your job is to kind of rewrite it first and see what you've really got. The one other kind of terrible situation with sines and cosines is if your powers are all even. So if you have the integral of like sine squared x times cosine squared x, you can't use a u sub. You have to use a trig identity instead. You have to let sine squared x equal 1 minus cosine of 2x divided by 2, and cosine squared x equal 1 plus cosine of 2x divided by 2. Which is always, nobody likes this part. It's always kind of gross. We do this, we get 1 minus cosine of 2x all over 2 times 1 plus cosine of 2x all over 2. This is kind of the nicest version of this problem because the middle terms end up canceling out. If I bring out the 1/2 and the 1/2, I have a 1/4 times 1 times 1 is 1. The plus cosine 2x and the minus cosine 2x cancel out. And then we have a minus cosine squared of 2x. Which then we have to use this identity again for. Now, if you want to be slightly slick, it doesn't really make that big a difference. But you could write this as 1/4 the integral of sine squared of 2x. Because 1 minus cosine squared of something is equal to sine squared of something. But it really, really doesn't make a big difference because then we still have to use this identity and say that sine squared of an angle is equal to 1 minus cosine of twice that angle divided by 2. So then we end up getting 1/8 the integral of 1 minus cosine of 4x. And here's exactly a situation where I wouldn't want to then compound this even further and have to do another u sub here. I'm just going to say I know the antiderivative of cosine of 4x. So I'm going to get 1/8 times x minus sine of 4x divided by 4. Let's see. Oh yeah. Okay, how much time have I got here? I still got almost a half hour. Cool. So let's look at secants and tangents real quick. The same idea is pervasive with secants and tangents. So secants and tangents, we explore the same sort of thing. If we have the integral of, say, secant to the fourth x, tangent to the sixth x. I honestly never know what I'm going to do here. I really just try both. I really think about trying both things. So here's my thought process. If I let u equal secant, my du is secant tangent. That soaks up one of the tangents, and I have an odd number of tangents left over. That's bad news. If I let u equal tangent, my du is secant squared. That soaks up two of the secants. I have an even number left over, and that's good news. So I should be letting u equal tangent. So if I let u equal tangent of x, my du is going to be secant squared of x dx. So if I rewrite this, I'm going to break off the du part. So I'm going to write this as secant squared x times tangent to the sixth x times secant squared x dx. You are not required to do it. I mean, you're not required to do anything the way I do it, right? You know this, right? You don't have to do it the way I'm doing it. I'm just trying to show you the way I think is the nicest way. But if you have a way that works better for you, do what works for you. There's my du, lovely. Tangent to the sixth is going to be u to the sixth. And then my even power of my not u choice, that's where my trig identity comes into play. So 1 plus tangent squared x equals secant squared x. So 1 plus u squared equals secant squared x, because u is equal to tangent. So that secant squared x is going to be exactly 1 plus u squared. And then we change it up. We write it as the integral of 1 plus u squared times u to the sixth du. You get the integral of u to the sixth plus u to the eighth times du, which is u to the seventh over 7 plus u to the ninth over 9. Let's see. Whenever you do a problem like this, where it's sines and cosines or secant and tangents or cosecants and cotangents, all of the powers of your trig function at the end should have the same parity. They should all be odd powers or all be even powers. You shouldn't have a mixture of odd and even powers, because they're always going to differ by 2 because of this trig identity, 1 plus u squared. Those differ by a power of 2. So anyway, here we get tangent to the seventh of x over 7 plus tangent to the ninth of x over 9 plus c. Just, we're not going to do this one, but I'll tell you, if you had something like the integral of secant to the fifth x tangent cubed x, here you would definitely let u equal secant x, because your du will be secant times tangent. That'll take away one of those tangents as well as one of the secants, and then you'll have an even number of tangents left over, and then you can use the same trig identity. And then I won't do it because we did it last time, but I'll tell you that the terrible case, like the integral of secant cubed or the integral of secant times tangent squared, this is where you have to do a trig identity and integration by parts, and then you do the stuff and you end up with the same integral at the end, and then you add it back over to the other side. We did this thing, we did at least one of these in class. I think we might have done both of them in class. So you should definitely go back and look at those examples. I should not do them again because they're tedious. They're actually not that tedious. They're just, I have a little bit of. So the other thing that's kind of weird that I always forget about is something like this. Yeah, I do not like this next example, but I will put it. So if you have like the integral of, say, sine of 5x times cosine of 7x. This is not something I know by heart. I would always have to look this up to figure out what to do. There is a identity for this. It's kind of funky. When you have sine of an angle times cosine of an angle, so sine of A times cosine of B, it's equal to 1/2 sine of A minus B plus 1/2 sine of A plus B. So we could think of our A as being 5x or B as being 7x and say that this integral is equal to 1/2 times sine of 5x minus 7x plus 1/2 sine of 5x plus 7x. And then use our usual skills here and get 1/2 times the antiderivative sine of negative 2x is negative cosine of negative 2x divided by negative 2. And then the antiderivative of sine of 12x is negative cosine of 12x divided by 12. And you could probably do some simplifying there, but that's how it's going to look. I don't think this is a identity you're expected to memorize. If something like this showed up on an exam, they would most likely be giving you the trig identity to be able to do it. It's certainly one I've never memorized in my entire life, and it comes up not that often, but often. Like there was someone doing a homework problem today asking me about this kind of identity. What else to say? There's something else I want to say here. It's keeping me. Oh yeah. Right. So someone just said their teacher used that in the sample exam. I think, although I don't recommend, but I think there's actually a way to do this via integration by parts. But I don't think it's what you really want to do. I think you should use the identity because it will be given to you. Okay. Continuing on. Sorry, everything that could be the last page. Sorry, 1 second here. My pages are all out of order. Oh, sure. Okay. Oh, yeah. There's some weird trig stuff on here. I feel like this got abbreviated here. Oh, yeah. We're totally missing the last part. I'm gonna find another version of this handout, which I know is more complete. The one I gave you is missing. So if we look here, just to kind of talk about this for a second. We've got the algebra stuff, many pages. And then we have the trig stuff, which we just kind of talked about. And oh, no, there's the mixtures at the end. I guess I must have dropped my last page here. Okay, good. So catching up to the last of the trig stuff here. Rational expressions involving sine or cosine seem super funky. Again, this is not an integral that I am expecting to see ever. But this example here, no, I feel like this example is not something I think you would see. Here's what you're supposed to do with this. I guess this seems really bonkers to me. They say to use sine of x equal to, oh, sorry, we're supposed to let u equal tangent of x over 2, and then sine of x is 2u over 1 plus u squared, and cosine of x is 1 minus u squared over 1 plus u squared. That seems totally normal, right? Not at all. This seems totally bonkers to me. And then you can put this all in here, and it just, yeah, no, don't do this. I've never seen this kind of question really ever. Like I can't say anything else. I mean, we could actually do it. It's done there, but like I don't see the value. Unless your teacher is coming at you with this kind of stuff. And I'm like, well, shoot. We talked about powers of tangent and secant. So in my opinion, the trig things that are most likely to show up are powers of tangent, cosine, powers of tangent and secants, maybe cosecants and cotangents, maybe the thing like sine of 5x, cosine of 7x kind of stuff, or maybe just stuff that can be simplified. For example, you might see something like the integral of, I don't know, let me think here for a second, sine squared x over cosine cubed x. And not have, I mean, I really have no idea how to do this, but I can start playing with it and see, well, sine over cosine another sine over cosine, another 1 over cosine. That's going to be it's going to be tangent times secant, which is that terrible integral I just mentioned before. Of course, I made up something on the spot that's awful, but doable, right? It is doable, but it'd be terrible. What I was kind of really going for was something more like the integral of cosine x over sine squared x. This one you could totally do as a u sub. You could let u equal sine of x, or you could rewrite it. I think the u sub is totally fine here, by the way, but you could rewrite it as cosine x over sine x times 1 over sine x, which is equal to the integral of cotangent x times cosecant x, whose antiderivative is definitely negative cosecant of x, because the derivative of cosecant is negative cosecant x times cotangent x. So a lot of times with trig stuff, it's just kind of playing around with it and seeing what you can make come up. It's often the u sub. Okay. Lastly, in our list of methods we have are mixtures. I should say types we have. So mixtures. So mixture meaning a combination of x to a power, a log, an e to the x, a trig, an inverse trig, stuff like that. Typically 2 of those types, usually not more, really. And so we often say 2 or more, but really it's almost always like kind of like exactly 2. Like it's x to a power and e to the x, or it's an inverse trig and actually nothing else, or it's an inverse trig and x to, like you're usually not getting like an e to the x and a sine x and a log of x. That's just going to be bonkers and probably not doable. So when it's a mixture, this is when usually either u sub or integration by parts is the right way to go. And it's kind of is it a composition of functions versus is it a product of functions? So for example, something like is the u sub, right? So if we have something like the integral of, I don't know, sorry, I'm making stuff up on the spot here. Sine of x times e to the cosine of x. This is a great time to do a u substitution because one of the parts, its derivative is equal to the other part. U is cosine, my du is negative sine. So negative du is equal to cosine of x dx. I want to be, sorry, I wrote the wrong thing there. Negative du is equal to sine of x dx. I want to be extra explicit here. U equal to cosine is the only correct u substitution. We could not pick u equal to, well, we could pick u equal to sine and be wrong, because then the derivative would be cosine of x times dx, and we don't have that. That cosine of x is stuck in the exponent. It is not getting multiplied by dx there. So here, if we did it this way, we'd end up with the integral of, there's my negative du, and then we have e to the u. So we get negative e to the u plus c, which is negative e to the cosine of x. Let's see. That would be our integral. So typically, if you see a function in another function, that's a good sign that we should try a u sub. Versus if we have something where it looks more like things multiplied together, like for example, the integral of x to the 4th times natural log of x. I don't see a composition of functions here. I don't see a function inside another function. I don't see a good u sub. So then, since I have a mixture, I'm going to then try integration by parts. But really, when I have a mixture, I first look for the u sub. I ask myself, is there something plausible? And if there isn't, then I go to integration by parts. So here, we're going to use the typical Lie8 acronym to pick our u. So we're going to pick u equal to the natural log of x. dv gets to be the rest. And then du is 1 over x dx. V is x to the 5th over 5. And we rewrite our integral as u times v, natural log of x times x to the 5th over 5, minus the integral of v times du, so x to the 5th over 5 times 1 over x dx. With integration by parts, the whole point is that the new integral that we still have to deal with should be easier to deal with. Sometimes it's going to require another integration by parts, but it's always something that should be simpler than the original. In this case, if we simplify, it's going to be something we can actually anti-differentiate. I'm going to bring out the 1/5, and then the x to the 5th divided by x is x to the 4th. And then if we integrate the x to the 4th, we're going to get the natural log of x times x to the 5th over 5 minus 1/5 times the antiderivative of x to the 4th is also x to the 5th over 5. Let's see. Now, I know this is only one example, and there's lots of different things that happen with integration by parts, but this is the general kind of idea, right? If you see a product of things, try integration by parts. There are a couple special cases for integration by parts. I would say, where are my papers right here? These 3 integrals are special. There's lots of special ones, actually, but here's a few special ones. The integral of the natural log of x, the integral of the arctangent of x, and the integral of the arcsine of x. All of these require integration by parts. And you only have one choice. You really have no choice here, right? It's not like it's a choice. There's only one thing you can do. You can let u equal the thing that's in the integral, either the natural log of x, or the inverse tangent of x, or the inverse sine of x. And then your dv has to be the dx part. I feel like these are noteworthy because people like to ask them, and it can be challenging to remember that this is what you have to do. It doesn't look quite like your typical integration by parts problem where you have a distinguishable one type of function and a second type of function. The dx here is playing the role of the algebraic or any power of x term. It just kind of. The other special one that just came to mind, as I said, special, is the integral of e to the x times cosine of x, or e to the x times sine of x. These are those ones where you have to do it twice, and then the same thing comes back up at the end. So integration by parts 2 times, and then add the original integral to both sides, or whatever constant multiple of that, depending on if you have like, not just if it's like e to the 3x cosine of 2x, it's a little bit more complicated, but it's still the same idea. Okay. I would now say that I feel like this list is fairly exhaustive. Obviously, we can't cover every case that's imaginable because you can always come up with something new. But this is a pretty good general outline of how you should approach integration. If it looks like this kind of thing, I should try this first, and then this, and then this, and then this, right? Usually the second or third thing you try should be the right thing, but it might not always be the first thing. Time is it? It's 4:20, but I am beat. Let's call it a day. Unless you, well, let's see. I'll call it a day. If you want to ask me some questions, you're welcome to. But I'm gonna stop the chat and stop the Zoom and rest my voice.